Welcome back to the energy conversion lectures. In a previous lecture, we have provided general introduction about the synchronous machine. In this lecture, we will continue our introduction lecture of synchronous machine by providing more information about the construction and some principal operation of synchronous machines. In general, synchronous generator and synchronous motor are identical from construction point of view. So same machine can work as a motor or as a generator. When the machine operates as a motor, we can say that the machine is in motoring mode. Also, when the machine operates as a generator, we can say that the machine is in generation mode. As mentioned in a previous lecture, the stator is made of laminated magnetic material core and windings. In practice, synchronous machine is usually a three-phase AC machine with three-phase windings. The three-phase windings called armature windings. The three-phase armature windings of synchronous machine can be represented by phase A winding, phase B winding, and phase C winding. Each phase winding consists of coils or at least one coil. In general, armature windings can be concentrated windings or distributed windings. Note that the armature windings use at least one coil just in case of concentrated windings type, as we will see during our discussion. Now let's give some idea about these two types of windings. Let's start with the concentrated windings. This figure shows front cross-section of two poles stator core used for the three-phase concentrated windings. This stator core represents the simplest form of the three-phase synchronous machine, which consists of 6 slots. These slots are used to house or install the three-phase armature windings. As we can see, phase A is implemented with only one coil, represented by coil AA', which have N turns. Coil AA' has two sides, side A and side A'. This figure shows how phase A coil is implemented if we open or flatten the stator core. Note that any coil with single turn will be represented as shown, while any coil with N turns will be represented as shown. The angle between the two sides of coil AA' is 180 degree in electrical angle. The angle can also be less than 180 degree electrical. The reason of shorten the angle will be mentioned in future lectures. Similarly, phase B winding is implemented with only one coil, represented by coil BB', which have N turns. Coil BB' has two sides, side B and side B'. Also, phase C winding is implemented with only one coil, represented by coil CC', which have N turns. Coil CC' has two sides, side C and side C'. Now let's focus on phase A. Phase A is implemented with only one single concentrated coil using N turns. Basically, phase A winding is called concentrated winding because it is implemented using only one coil of N turns. Each side of the coil is installed or concentrated in only one slot. Note that phase B and phase C are implemented in same way as phase A. It should be noted here that this stator represents two poles stator because each phase produces magnetic field equivalent to the magnetic field produced by two magnetic poles. In other words, each phase produces two poles. Let's explain this point using this single-phase machine which have cylindrical rotor. If a current I flow through phase A winding in this direction, phase A will produce magnetic field equivalent to the magnetic field of two magnetic poles shown. Note that if we excite phase A with AC current, these two poles will alternate between south and north poles. At this point, we should know that in case of this three-phase stator, each phase will produce two poles when it is excited. Therefore, this stator represents two poles stator. In general, we can say that the number of poles of synchronous machine stator is equal to the number of poles per phase. It is very important to know that the three-phase windings of synchronous machine are shifted from each other in space by 120 degree in electrical angle as shown. As mentioned in a previous lecture, the electrical angle theta E is equal to P over 2 times the mechanical angle theta M, where P is the number of poles. Note that the electrical angle and the mechanical angle are equal only in case of two poles stator or machine. The electrical circuit diagram of these two poles three-phase concentrated armature windings can be modeled as shown. In practice, armature windings of synchronous machine are connected in star connection as shown. This figure shows four poles single-phase stator with cylindrical rotor. As we can see, this single-phase stator winding represented by phase A. This four poles single-phase stator winding consists of two concentrated coils, coil A1 A1' and coil A2 A2'. These two coils of phase A can be connected in series or in parallel as shown. Basically, this single-phase stator represents four poles stator because these coils produce magnetic fields equivalent to the magnetic field of four poles when it is excited as shown. Note that the angle between the sides of each coil is still 180 degree in electrical angle. These figures show four poles three-phase stator with concentrated windings where each phase consists of two coils connected in series. It should be noted here that in case of concentrated windings, the number of coils of each phase is equal to half the number of poles. So in case of four poles stator, the number of coils of each phase is equal to 4 divided by 2. Therefore, the number of coils of four poles stator is equal to 2 coils per phase. The other way to confirm the number of poles or number of coils of the concentrated windings is by inserting four poles rotor inside the stator and prove that each rotor pole facing one side of the phase coils of the stator, as shown in this example. As we can see, At this rotor position, this north pole facing A1 side, this south pole facing A1 side, and this north pole facing A2 side, and this south pole facing A2 side. Now let's give some idea about the distributed windings. In general, distributed windings means that each phase winding consists of more than one coil. These phase coils are connected and installed in slots distributed in the inner surface of the stator. Let's give some details about this definition. These figures show an example of two poles stator core used for the three-phase distributed windings. The three-phase stator core in these figures consists of 12 slots used to house or install the three-phase distributed windings. As we can see, phase A winding is implemented by using two coils. These coils are coil A1 A1' and coil A2 A2'. These coils always connected in series. Similarly, phase B winding is implemented with two coils B1 B1' and B2 B2' connected in series. Also, phase C winding is implemented with two coils C1 C1' and C2 C2' connected in series. As we can see in this example, each phase is implemented by using two distributed coils. Each phase coil has n turns. Basically, phase A, phase B, and phase C windings are called distributed windings because each phase is implemented by two coils of n turns. Each side of the coils is installed in two slots. It should be noted here that this stator represents two poles stator because each phase produces magnetic field equivalent to the magnetic field of two magnetic poles. In other words, each phase produces two poles. For example, if a current flows through phase A winding in this direction, phase A will produce magnetic field equivalent to the magnetic field of two magnetic poles shown. Similarly, phase B and phase C are also producing magnetic fields equivalent to two poles as well. These arrows represent the magnetic field direction or axis when the phases are excited by currents in the direction shown. In general, the number of poles of the stator or machine is equal to the number of poles of any phase. Again, the three-phase distributed windings of synchronous machine are shifted in space from each other by 120 degrees in electrical angle. The electrical circuit diagram of these two poles three-phase distributed armature windings can be modeled as shown. This figure shows four poles single-phase distributed stator where the phase consists of two groups of coils. In this example, each group consists of two coils, always connected in series. These two groups of coils can be connected in series or in parallel. This single-phase stator is representing four poles because these two groups of coils produce magnetic fields equivalent to magnetic field of four poles, two north poles and two south poles as shown. Note that the angle between the sides of each coil in these two groups is 180 degree in electrical angle. This figure shows an example of the three-phase stator windings of 4 poles where each phase consists of two groups of coils connected in series, and each group consists of two distributed windings. This figure shows how these 4 poles distributed stator windings are implemented if we open or flattened the stator core. It should be noted here that the armature windings of the practical and industrial synchronous machines are distributed windings. There are two main reasons of using armature distributed windings instead of concentrated windings. The first reason is that in a practical machine, the induced voltage of the armature windings needs to be large and appropriate value. So if we use the concentrated winding, a very large number of turns are needed in each phase. Therefore, it is not practical to accommodate all these turns of each phase in one slot of coil sides of the concentrated stator core. To resolve this issue, distributed windings are used. The distributed windings use many slots to accommodate many coils of each phase and therefore able to build machine that can withstand high induced voltage. The second important reason of using distributed windings is that the distributed armature windings produce magnetic field distribution in the air gap close to sinusoidal waveform, while the concentrated armature windings produce rectangular magnetic field distribution in the air gap. Let's give some idea about this point. Assume we have these two single-phase machines, one with concentrated 2 poles stator windings and the other with 2 poles distributed stator windings. Both have cylindrical rotor which create uniform air gap with the stator. In case of the single-phase concentrated winding stator, if we excite the winding with DC current I in this direction, a magnetic field will be produced as shown. Let's ignore the impact of the magnetic cores by assuming the permeabilities of the cores are infinity. Now let's assume that the air gap magnetic field from the stator to the rotor is positive and representing the north pole of the stator. Also, let's assume that the air gap magnetic field from the rotor to the stator is negative and representing the south pole of the stator. Now, if we have a measurement device for the magnetic field magnitude and we start to measure the magnetic field magnitude at different points around the circumference of the stator starting from gamma equal to 0, the magnitude of the magnetic field can be plotted as shown. Note that the angle gamma represents the angle of different position around the circumference of the stator. Basically, this waveform, denoted by Fa, represents the magnetic field distribution generated by the phase A concentrated winding, which obviously looks like rectangular distribution waveform. So this rectangular waveform represents the nature of the magnetic field distribution of the concentrated winding. Note that this waveform represents the nature of the magnetic field distribution of 2 poles stator concentrated winding. The magnetic field distribution of 4 poles single-phase concentrated winding is as shown. As we can see, within full cycle, the cycle has 4 poles, 2 north poles and 2 south poles. Now, if we repeat the same procedure to the distributed winding, we can find that the magnetic field distribution looks like sinusoidal distribution waveform as shown. So we can notice that the nature of the magnetic field distribution of the distributed winding is close to sinusoidal waveform. It is very important to know that having sinusoidal magnetic field distribution is very important to achieve sinusoidal terminal voltage and current with very minimum harmonics. Also, the sinusoidal magnetic field distribution improves the torque production of the machine because it avoids the unwanted pulsating torque components that can be produced if the magnetic field have harmonic components. It should be noted here that the ideal output torque generated by the machine is average value or constant value. So any component on top of the average generated torque can be called pulsating torque components. At this point, we should be able to understand that there is a direct relationship between the machine construction and the air gap magnetic field distribution. The air gap magnetic field distribution of synchronous machine will be provided in details in the upcoming lectures. At this point, we got some idea about the magnetic field distribution when we inject the DC current to the single-phase armature windings. The question now, what happens when this AC current I is applied to this single-phase armature distributed winding? As we can see, the AC current magnitude changes with the time. When the current magnitude at time t1 is applied to the stator winding, the single-phase stator poles will be as shown. The stator single-phase magnetic field waveform of the excitation current of instant t1 can be represented as shown. When the current I change to instant t2, the stator poles and magnetic field will be as shown. In case of current at instant t3, the stator poles and magnetic field are as shown. In case of current at instant t4, the stator poles and magnetic field are as shown. In case of current I at instant t5, the stator poles and magnetic field are as shown. In case of current I at instant t6, the stator poles and magnetic field are as shown. In case of current I at instant t7, the stator poles and magnetic field are as shown. Basically, the stator poles generated by single phase will be alternate between south and north poles as the AC current changes in magnitude with time. Also, the magnitude of the magnetic field waveform will be alternate as the AC current change in magnitude with time. It is very interesting to know that the magnetic field waveform distribution is not traveling. That means there is no shift to the right or left in the magnetic field waveform of the single-phase stator winding when it is excited by AC current. Note that the waveforms with such behavior can be called standing waveform or non-rotating waveform or not traveling waveforms. It is very important to know that the three-phase armature windings of the synchronous machine carry three-phase AC currents. Note that we used here concentrated windings to simplify the drawing. However, we are still going to assume that the magnetic field distribution is close to sinusoidal waveform. These three-phase AC currents are shifted from each other in time by 120 degrees in electrical angle. It is very interesting to know that the three-phase AC currents flowing through the three-phase armature windings will produce a stator rotating or moving magnetic field in the air gap. This rotating magnetic field, which denoted by Fs, has constant magnitude even when the three-phase AC current's magnitude changes with time. Basically, when the phase currents pass through the phase windings, each phase of the three phases will generate standing waveform or non-rotating waveform. As mentioned earlier, the standing waveform's magnitude change as the current magnitude change with time. The three-phase standing waveforms can be denoted by Fa, Fb, and Fc. The vector sum of the resultant of these three-phase magnetic field standing waveforms will generate the rotating or moving magnetic field waveform Fs, which has constant magnitude. It is very important to know that the stator rotating magnetic field Fs is rotating at synchronous speed ns. Note that the three-phase standing magnetic fields Fa, Fb, and Fc are shifted from each other by 120 degree electrical. For this two-pole stator machine, the stator rotating magnetic field Fs can be represented by these two yellow poles, which are rotating or moving in the air gap at synchronous speed ns. Note that these two yellow rotating north and south poles are not actual or physical poles. However, we just use them to visualize the stator air gap rotating magnetic field Fs. This waveform shows the stator rotating magnetic field waveform Fs at theta s equal to 0, where theta s represents the stator air gap rotating magnetic field position. The angle gamma represents the angle around the stator circumference. This waveform shows the stator rotating magnetic field waveform Fs at theta s equal to 30 degree. This waveform shows the stator rotating magnetic field waveform at theta s equal to 90 degree. Note that this stator air gap rotating magnetic field rotate or move from position to other position at constant speed, which is the synchronous speed ns. Also, we can notice that the magnitude of the rotating stator magnetic field Fs is always constant. We would like to emphasize here that the rotating magnetic field is represented here by the two rotating poles because the stator in this example is two-pole stator where each phase generates magnetic field equivalent to two poles as mentioned earlier. So, in case of four-pole stator shown, the rotating magnetic field can be represented by four rotating poles as shown. The rotating magnetic field generation of the stator will be discussed and proven mathematically in details in separate lecture. Now let's pay attention to this point. When the stator rotating magnetic field Fs links the armature windings, an induced EMF voltage will be produced in each phase. The three-phase induced voltages EAS, EBS, and ECS in the armature windings can be called armature reaction induced voltages and can be represented by Vs, where Vs represents the RMS value of any of the three-phase voltages. Please note that this induced armature voltage Vs does not represent the main induced voltage of the machine. We will learn later that the main voltage component or the larger voltage component of synchronous machine is generated by the rotor rotating magnetic field and not the stator rotating magnetic field. Now let's move to other important principles about the synchronous machine operation. Assume we have the following salient pole synchronous machine. This machine represents two-pole synchronous machine. When a DC current flows through the field winding of the rotor generates DC magnetic field and becomes electromagnet as shown. Let's ignore the impact of the magnetic cores by assuming the permeability mu of the magnetic materials are infinity. So the focus will be at the rotor air gap magnetic field. Now let's pay attention to the following point. The rotor core and the rotor winding of the machine must be designed in such a way that the rotor magnetic field has sinusoidal shape or sinusoidal distribution in the air gap. Let's explain this point. Let's divide the machine into two sides. The left side facing the rotor south pole and right side facing the rotor north pole. Also, let's assume that the rotor air gap magnetic field flowing from the stator to the rotor is negative and the rotor air gap magnetic field flowing from the rotor to the stator is positive. Now if we measure and plot the air gap magnetic field at different points around the stator circumference starting from gamma equal to 0, we can identify that the shape or nature of the air gap magnetic field distribution is close to trapezoidal waveform as shown. As we can see, the air gap magnetic field is constant value or flat in front of the pole face because the air gap is small and constant in this area. Also, we can see that the magnetic field starts to decay at the sides of the pole face because the air gap is large. Obviously, this waveform is not sinusoidal and it has lots of harmonics. We mentioned earlier that the goal is to design the rotor with sinusoidal air gap magnetic field distribution. Therefore, in future lectures, we will need to learn how to achieve sinusoidal rotor air gap magnetic field distribution. It should be noted here that the nature or shape of the rotor magnetic field distribution is directly impact the quality of the armature induced voltage, current, and torque of the machine. Again, this topic will be covered in details in future lectures. Now let's pay attention to the following. When the rotor is excited and then somehow rotate mechanically, the DC magnetic field generated by the DC excitation current will rotate as well. That means the combination of the DC excitation of the rotor winding and the rotor mechanical rotation will produce a rotor rotating magnetic field which can be represented by the vector Fr. This waveform shows the rotor rotating magnetic field waveform Fr at theta r equal to 0, where theta r represents the angle of the rotor air gap rotating magnetic field position. The angle gamma represents the angle around the stator circumference. This waveform shows the rotor rotating magnetic field waveform Fr at theta r equal to 60 degree. This waveform shows the rotor rotating magnetic field waveform Fr at theta r equal to 90 degree. So now it is obvious that these figures show how the rotor magnetic field Fr is rotating or moving with rotor movement at different rotor position. As we can see, each of these plots has been generated from a particular rotor position angle. Now let's pay attention to this point. The rotor air gap rotating magnetic field Fr will link with the three-phase stator winding or armature windings and produce an EMF voltage in each phase EAR, EBR, ECR. These induced EMF voltages EAR, EBR, and ECR generated by the rotor rotating magnetic field Fr represent the main voltage component of the machine and can be represented by ER, where ER represents the RMS value of any of the three-phase voltages. It is very important to know that the shape of the induced armature voltage waveform is impacted by the rotor air gap magnetic field shape or distribution. That means if the magnetic field distribution is non-sinusoidal, the armature induced voltages will be non-sinusoidal as well. Also, if the magnetic field distribution is sinusoidal, the armature induced voltages will be sinusoidal. Now let's summarize some important points about the armature or stator induced voltage. When three-phase balanced armature currents pass through three-phase armature windings, a stator rotating magnetic field in the air gap will be produced. This stator rotating magnetic field will link the armature windings and induce voltages in the armature windings. Also, when a DC current flows through the rotor field winding plus rotor mechanical rotation, a rotor rotating magnetic field will be produced. This rotor rotating magnetic field, Fr, links the armature windings and induces voltage ER in the armature windings. Now let's pay attention to the following. The vector sum of the stator and rotor rotating magnetic fields will produce the total rotating magnetic field in the air gap FSR. Also, the vector sum of the stator induced voltage Vs and the rotor induced voltage ER will produce the total terminal voltage of the armature windings VTA. This important concept of air gap rotating magnetic fields and induced voltages of the machine will be discussed mathematically in details in the future lectures. Note that this concept is applied to both synchronous generator and synchronous motor. At this point, we already provided some idea about the rotating magnetic fields of the stator and rotor. Also, we mentioned that the induced voltage in the armature windings is induced because of the stator and rotor rotating magnetic fields. Now let's give some idea about the torque produced by the machine. Let's first define some important torque terms. The torque generated by the machine is usually called electromagnetic torque and can be represented by Te. The torque generated by the turbine or any external mechanical device connected to the synchronous machine is called mechanical torque and can be represented by Tm. Basically, we are going to focus on the electromagnetic torque generated by the machine. In general, there are two important conditions to develop the electromagnetic torque in any machine. The first condition is that the electromagnetic torque of the machine is produced only if both stator and rotor magnetic fields have same number of poles. In other words, the stator and rotor must have same number of poles. The second condition is that the magnetic fields of the stator and rotor must be stationary with respect to each other. This applies to all types of machines. So in case of synchronous machine, the stator and rotor magnetic fields are both rotating at the same speed, which is the synchronous speed. Therefore, both magnetic fields can be considered stationary with respect to each other. It is very important to know that the interaction between the stator rotating magnetic field Fs and the rotor rotating magnetic field Fr will produce the electromagnetic torque Te of the synchronous machine. In other words, the electromagnetic torque Te of the synchronous machine is produced because the rotor and the stator rotating magnetic fields trying to align themselves with each other. Basically, the stator rotating magnetic field behaves as magnet and the rotor rotating magnetic field behaves as magnet as well. These two magnets attract each other and aligned. Now, if the two magnets are misaligned by external mechanical torque Tm, the two magnets will produce counteract electromagnetic torque to avoid further misalignment. Let's explain this concept for both the synchronous generator and synchronous motor. Let's first discuss the synchronous generator case. This figure shows two poles three-phase synchronous generator. As mentioned before, when the rotor winding is excited by DC current, the rotor becomes electromagnet with two poles. Now assume a mechanical torque Tm is applied by a turbine connected to the rotor shaft in this direction. Therefore, the rotor will rotate at certain speed ns in this direction. Note that the torque Tm at this point is very small because the electrical load is not connected to the machine yet. In other words, there is no resistance against the turbine rotation. As mentioned earlier, the combination of the rotor poles and the mechanical movement will produce the rotor rotating magnetic field. The rotor rotating magnetic field can be represented by the vector Fr in the direction of the rotor magnetic field axis. As mentioned before, this rotor rotating magnetic field Fr will link the armature windings and induce the main voltage component in the armature windings. Now, if a light or small electrical load is connected to the machine, a small stator current will start to flow to support the light load. This stator current will generate the stator rotating magnetic field. Note that the stator rotating magnetic field will be represented by these two yellow rotating imaginary magnetic poles. The stator rotating magnetic field can be represented by the vector Fs in the direction of the stator rotating magnetic field axis. As we can see, both the stator and rotor magnetic fields will be aligned and rotate at same shaft speed and direction because the load is very small and almost no electromagnetic torque is produced by the machine. Now, if the electrical load is increased to large level, the stator rotating magnetic field will be shifted behind the rotor rotating magnetic field as shown. In other words, the stator magnetic field will be lagging behind the rotor magnetic field. Under this condition, the machine will produce electromagnetic torque Te acting on the rotor in this direction and trying to avoid further misalignment between the two rotating magnetic fields. Therefore, the stator and rotor fields will still be rotating at same speed. Note that the torque Te is generated from the fact that the rotor and the stator rotating fields attract each other and the two magnets trying to be aligned. So a large torque Te is developed by the machine when a large electrical load is applied. The torque Te will try to slow down the machine or rotor speed. Therefore, a mechanical load Tm which produced by the turbine must be increased and balances the torque Te to keep and maintain the original synchronous speed Ns. It is worth to mention here that in generator mode, the direction of the electromagnetic torque Te developed by the generator is in opposite direction to the rotor rotation and opposite direction to the mechanical torque Tm. Now let's move on to the synchronous motor case. This figure shows two poles three-phase synchronous motor. Assume that the motor is not connected to the mechanical load yet. Now when three-phase armature currents are supplied to the stator, a stator rotating magnetic field will be produced. Note that the stator rotating magnetic field will be rotating at certain speed Ns. Let's assume that the rotor magnetic field is already established by certain field current and the rotor poles start to rotate and follow the stator rotating imaginary poles. It should be noted here that the synchronous motor is not self-start machine, but at this point we just assumed that the rotor started by some method and followed the stator imaginary rotating magnetic poles. As we can see, the stator and rotor rotating poles are rotating in this direction at speed ns and they are aligned or locked with each other when there is no mechanical load connected to the machine shaft. Under this operating condition, the machine produces around 0 electromagnetic torque Te when the mechanical load is not connected. Now, once a large mechanical load is applied or connected to the machine shaft, the mechanical load torque Tm will oppose the rotation of the rotor. Therefore, the rotor rotating magnetic field will lag behind the stator rotating magnetic field. Under this condition, the machine will produce electromagnetic torque Te acting on the rotor in this direction and trying to avoid further misalignment between the two rotating magnetic fields. Note that the torque Te is generated from the fact that the rotor and stator rotating fields attract each other and two magnets are trying to be aligned. Therefore, the stator and rotor rotating magnetic field will be still rotating at same speed ns. Since the two magnetic fields are still rotating at the same speed, the angle between the two fields will remain same at steady state. It is worth to mention here that in motoring mode, the direction of the electromagnetic torque Te, which developed by the motor, is in the same direction of the rotor rotation. Also, the torque Te opposes and balances the mechanical load torque Tm. We would like to mention here that whatever information provided in this introductory lecture are just general overview to highlight the importance of the magnetic fields in producing the armature induced voltage and electromagnetic torque of the synchronous machine. The details and mathematical derivation of the machine operating concepts will be provided in the future lectures. Let's conclude this lecture at this point and will continue in the next lecture. Let me know if you have any question. Also, make sure to subscribe to this channel so you do not miss any lecture. Thanks for listening. I am Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.